So the essential question, how can we use resolution of vectors to add vectors? So first we said that, we can get basically an idea about what the result and what the sum of these vectors is going to look like if we can kind of translate this one in space, put it head to tail with this one. And so I'll try to sort of do that here. So this one would kind of go over like this, and it goes like that, right? That's the same as this one, almost. And so the resultant would be or that one right there. So A plus B, when you put them head to tail, connect the tail of the first and the head of the last, sort of that should be sort of our resultant there. And we kind of looked at yesterday. Here we want to use the resolution of vectors so we can resolve the vector into its x and y components. All right. So let's take a look at that. Let's say that this blue vector let's make it a displacement vector, and let's say that the angle here was 32 degrees, and that the magnitude of it was 7 meters. 7 meters, 32 degrees above horizontal. Okay, so that's the sort of information we get about this vector. Vector B over here, has a component that goes to the right and has a component that goes down, just like I can draw components of vector A that go to the right and up, because it points up to the right, this one points down to the right, so it has components that are corresponding in those directions. And let's say that this angle here was 49 degrees, okay, below the horizontal. So you could say, well, if we do everything relative to the positive x-axis, then it's like this angle right here, which we could do 360 minus this and have it. And then it will the calculator will deal with the negativity of this vector for us. Like if you plug in your calculator, always relative to the positive x-axis, then your calculator will understand that this is pointing down because it sort of defines everything relative to this. I almost prefer to think like a human being rather than a calculator and just say, well, if that's the angle right there at 49, I can see that it's pointing down, make it negative. But here's where we can kind of, let me elucidate this point with the calculation. Like, go here with my wires. Calculator handy. So the vector B here is like, if that's 7, then that's like 15 meters, let's say. But I want to know how to resolve these vectors. I want to break it down into the right and to the down sort of components. Let me focus on this down component. It's better for me to realize that this side is opposite this angle, and I know the hypotenuse is 15. So I relate opposite the hypotenuse with the sine function, and I'd say the sine of this angle is equal to the thing I want to know over 15. I solve for what I want to know. So that's going to look like this. The sine of 49 degrees is equal to, let's call this the y component of B. The opposite over the hypotenuse, which remember is this, right? That is the vector is like the hypotenuse. We draw legs to force it into a right triangle, right? We're drawing x and y components. So this is 15 meters. And so the y component of B is the sine of 49 degrees times 15 meters, which is, everybody with a calculator knows that the sine of 49 degrees times 15 meters is, e-learners, unmute your mic and call it from above. Come on, e-learners. You're making me look foolish right now. So we didn't need to give you any help for that. You wearing a face shield for the sake. I'm saying shield and recognize.
11.32.
11.32, I heard. Well, it wasn't like a booming voice from above, but I need to just turn the volume. 11.32. Note how the calculator didn't tell me that's negative going down. Okay, that's because I gave it 49. This is like opening downward. Okay, like, what's this angle right here? Anybody know what this angle right here is? $311 degrees. If I were to say this angle right here is 311 degrees, and I gave you just a minute or two or a moment or two to think about how Jordan calculate that, you should be able to go, oh, I see it, I see it. And if you're like, oh, see how you got that, you need to raise your hand and go, how did Jordan? Anybody not know where this value is coming from? 311, Ewan, there. 360 degrees all the way around, right? So that much is 49, and that much is 311, like 360 degrees in a circle. So let's do the same calculation, but this time do sine 311. Okay, times 15. Do that real quick. Find what you got. See that? Okay, so if you always sort of plug in the angle relative to the positive x-axis, you don't have to think like a human being. The calculator like thinks for you, says it's negative there, it's pointing down. All right. We can look at this and see that it's down, right? And just make that negative if we need to. That's the point. Like, my personal opinion, I'd rather look at a triangle and do my trigonometry. That's the 49-degree angle in my triangle. And I can see that it's down, okay? But if you're like, well, I want the calculator to do that for me, then you have to always sort of align your angles relative to the bottom of that, like opening upward from the side. So anyway, the component here that's going, down is 11.32. Of this 15 meters going this way, 11.32 meters going down. Does that just mean that 15 minus this, the other 3 and whatever must be here? Is that the way that we solve that? No, it's not this plus this equals this. It's this squared plus this squared equals this squared, right? Pythagoras is down. That's the way we have to sort of relate how these sides are related in this right triangle. Okay. So here we've got d sub y equal to 11.32 meters. Make it negative if you like. Okay, pointing down. Yeah. Let's do this component up here. D sub x. Take just a minute and see if you can think your way through that calculation. Okay. Set it up. Crunch some numbers. When you've got a number in your calculator, I want to see if you call it out if it's the same number I got in my calculator. Got it. So I want to know what is the x component, the horizontal component of vector v, given that it's opening down 49 degrees and the magnitude is 15 meters. Direction, magnitude, vector. Vector addition, right? So only add vector. We could add scalars to either that, errors like this. Everybody with a firm grasp of the learning objective and a calculator in hand knows that the x component of v is a voice from above, a booming voice resounding throughout the lab says, in-person students, you can be the booming voice from the lab. Okay. I'm recording this, you guys need to look at all the YouTube friends. Multiplier, chat wild play. Shout out to the spine ninjas and chat wild play. We are the spine ninjas, you guys. I got first grade at home.
9.84.
9.84.
Meters.
Meters, well done. I was like, the units are so important, guys. Well done, well done. There's a couple of students in class that are looking, oh, why didn't I say it? I had it. No, don't be afraid to offer an answer, even if it's incorrect. It's okay to be wrong. Dad say, oh, you're wrong. Check it. Put the button wrong. It's good to make mistakes now. You make mistakes now, you'll learn from them. Come to test, you'll say, oh, I made that mistake before, I won't make it now. All right, so learning from mistakes is a great way to sort of improve. So it's okay to make mistakes, and don't be hesitant to sort of call out an answer. If I want to know what is R, all right, and I'm adding A and B. I know that B was this vector that's got like, it goes down and to the right, it goes to the right 9.84, it goes down 11.2, and 9.84 squared plus 11.32 squared is equal to 15 squared, like Pythagoras' theorem for the factors of relationship between those. We can do that in reverse. If vector A brings us up and to the right, and vector B brings us to the right and down more than A brought us up, then R should have a net down component and a net right component that we can calculate by just summing like the up plus the down to get this, the net down, the right plus the right to get the net right, and we'll have these. And then we can use Pythagoras' theorem to deduce the result of R. That's how we use resolution of vectors to add vectors. To resolve each vector into its x and y components, you add up the x's, you add up the y's, you draw a new triangle, right? Where now I got the sum of the y's for this, the sum of the x's for this. And then I can use Pythagoras' theorem to calculate the hypotenuse R. Okay, so that's what we want to do now. You all get a head start. We've already resolved one of them. This is resolving a vector. You know the hypotenuse, you know the angle. That's enough to resolve it if you know your SOAP and your trick. If anybody's like, I don't see how you got 9.84, and this isn't still too clear, that's fine. Like, don't feel like, oh no, I don't belong in this class, or it doesn't make sense to me. There's plenty of students that, it doesn't make sense to them at first. I remember, I always kind of share this story. I failed miserably. Everybody else heard it too, right? Well, today's the day. Finally happened. I lost my whole train of thought. We got to start over now. Why safety first? Not that far back. We got to start at the beginning of time. I'll start with a big bang. 15 billion years later, here we are adding that. Right. Okay. I just remind myself. Oh, I failed miserably. College trigonometry. I didn't know how to solve for the angle. It was like giving us the sides. I'm like, I want to solve for the angle. I kept on failing quiz after quiz. I mentioned with my professor, I'm like, I don't know why I'm against such bad grades. It's like I can solve for the sides, but I don't know how to solve for the angle. So you got to use the inverse trick. Remember we did that the other day? It's like the inverse tangent solve for the angle. I'm like, oh, so I failed half a semester of college trig because of this button right here. Just push a button. That was I mean, so it's like, okay, you don't know until you know it. Everybody learns in slightly different, cases. And I must have been absent-minded that day where they went over them. I didn't know until I asked the question. So here, we're just using the definition of trig, right? The definition of the sine is that the sine of the angle is equal to a ratio, the opposite side length divided by the hypotenuse. And so 11.32 divided by 15 is the sine of 49, right? 11.32 divided by 15, that's equal to the sine of 49. You can evaluate that in your calculator, and you'll find that number, whatever it is, sine 49, is also equal to 11.32 divided by 15. Okay, that's sort of like, there's rules to triangles. If I draw a line, And I want there to be a right triangle with this line. There's only certain side lengths that will work, right? Like there's rules to triangles, and those rules are captured within these functions. That's one of the things that trig functions do. So it's like, you know, if I have a stick and I want to turn that stick into a triangle, I need to find sticks that are exactly that long and exactly that long. That stick's too long. There, now it's the right one. You see what I'm saying? So like, you can't just choose any old side lengths to work here. Only certain lengths are going to work to close that triangle. And so that's why like the sine of this angle is equal to this ratio of sides, because it's sort of it's capturing that sort of mathematics. Right? So this answer here was what? That's the adjacent side. That's the so this is adjacent. The cosine of 49 times 15. See how computationally it just ends up being hypotenuse times either the sine or cosine of the angle. But set it up like this version. It is my strong recommendation to you to like set it up with the trig definitions in mind before you just start saying, oh, the vertical one's always the sine, the horizontal one's always the cosine. That's only true because we've aligned it relative to the problem. That will change once we get problems that are tougher, like here's a block on a ramp, and now the angle is here relative to the y-axis. That's going to change everything. So I don't just try to do something clever like, oh, vertical is always sine. For this part, you know, it will be. I mean, provided we always align it to the positive x-axis, that will be true. But we won't always align our angles to the positive x-axis. So just like we set up this one to figure out b sub y, we got this answer. There's a few students in class that are really confident about this. They calculated, they got 9.84, that's correct. But we're not quite there. Let's sort of think about this. I wanted to know this. I know the hypotenuse, I know the angle. Because I want to know the side adjacent. Remember this. The sine relates opposite to hypotenuse, the cosine relates adjacent to hypotenuse, the tangent relates opposite and adjacent. All right, so this is your shortcut, your mnemonic device to remember all the trigs. And if you want to, you can couple that with a all right, here's the key to the whole class right here. That's all you need. Let me erase it now. Okay. You got theta, you got the hypotenuse, you got the side opposite, you got the side adjacent. Like this plus this equals trig. That's what we're doing with this related sine, cosine. So the cosine of our angle theta, which is 49 degrees, equals adjacent, which I didn't know, let's call it the x component of b, and the hypotenuse, still 15, just like it was here. And so in your calculator, you can evaluate cosine of 49 degrees, that's some number, right? And we know, based on the trig, based on the rules of triangles, it's equal to this over that. So that's how we used it to solve for this. And if you didn't already practice this calculation, if you've got a good scientific calculator, use that in class. Okay, if you're like, I don't bring that to class, but I have my phone which has a nice scientific calculator, use that. But try to remember to bring one of these with you because I want to allow you to use your phones on testing too. Okay, because while your phone is a scientific calculator, there's a lot of other things too. You know, practice using the one that you're allowed to use on the exam. Okay, so you don't need like a graphing calculator, you just need a scientific calculator with the trig functions. Okay, it's like $10. So please bring one the day of the final exam. It's so frustrating. I mean, every year, it's like, all right, final exam, physics. We've been studying all year for this. I didn't bring a calculator. Well, why? Physics exam, you need one. All right. So if you multiply both sides by 15 meters, you'll solve that. The x component of b was 9. That's how we do it. Just multiplying both sides by 15. So I was like, don't just go right to this. Like set up, you know, the ratio of sides based on the definition of trigonometry from this. And you'll tend to make less mistakes. And then once you get more comfortable with it, you're like, oh, it's always, you know, it always kind of looks like that. Let's do the same thing for A. If you haven't already done so, some students are like, anticipated that we would be doing that, right? Because we're solving for R. So let's go ahead and break A down. I'm going to sort of translate it in space over here. To remind myself that it's a 32-degree angle above the horizontal and it's 7 meters long. So given a hypotenuse and an angle, you should be able to resolve the vector, we say, into its perpendicular components, into its horizontal and vertical components. Since that vector is A, we'll use the same convention calling that A sub y, A sub x. Let me know when you got it, you learners. What do you learners? Also, if everybody following along on YouTube, just leave it down in the comments below. Don't forget to hit that like button and subscribe. So chat wild for Who got? We are the spine ages as the answer. I feel like that's pretty adequate wait time. Some students still calculating. I think I hear some of you learners still crunching some numbers out there, even though their microphone is muted. Still here. Who knows either the y or the x component of A or both by show of hands?
3.7 meters.
Follow-up question. Yes. Well, there is a follow-up question. What is the y component of A? Oh, or 3.71. Anybody else get that? Anybody get the x component of it? I got these. 3.7, 5.9. So here's a good time to ask a clarifying question. If you're like, can you show us that again, like you did with this, or like it's the exact same kind of thing that we're doing here, right? So it's, I want to know the opposite side. So the sine of this angle, let's write it all out. The sine of the angle, it's always the function of the angle, right? Sine of the angle equals the thing I want to know over the hypotenuse. Multiplying both sides by 7 meters, you can solve that the y component of A should be 3.7 meters. And doing the calculation for yourself in class, or if you're following along at home, will build your confidence that you're doing it correctly when your calculator displays 3.71 or whatever it is. We'll just round it. I mean, just like in chemistry, you kind of look at significant digits and say, well, I only know this is 2 significant digits, so let me kind of keep my answers. The x component is adjacent to the angle, so really like relative to the angle, right? That's where the opposite adjacent hypotenuse. The hypotenuse is always the side opposite the right angle, right? So the other two sides are either next to the angle in question or opposite. We're never looking at the right angle itself. Okay, we're always looking at this angle or that angle. And so it's true that like if this is 90, this is theta, this is what 90 minus theta, they have to add up to 180 degrees. So like the sine of this angle is equal to the cosine of that angle. That will always be true also. In other words, we could have solved for this side as considering an opposite from this angle. If this is theta, we call some other angle phi. So in physics, it's like every angle is theta, unless there's two angles, then there's theta and phi. Phi looks like that symbol up there for your person. Don't worry, you learners, I got it. That piece of paper up there. There's a phi. Okay, that's a high phi. A high phi. Just high up from the wall. I used to have a rho down here, a low rho. Rho is a letter that looks like kind of like a P. And it stands for everything in physics. It stands for density, it stands for resistivity, lots of things that rho stands for. So a low rho and a high phi for the physics lab. I think that's a mental note. So get my low rho back here. I think it got like swept away. So anyway, if we use this angle phi to solve for like this side right here that used to be adjacent to theta, well now it's opposite from phi, right? It's still the same triangle though. So it, you know, the cosine, I'm sorry, the sine of this would be opposite. The cosine of this is adjacent. So it's like the cosine of phi is the sine of phi. The cosine of theta is the sine of phi. All right, if that makes sense to you, awesome. If it doesn't, I'll go over it so much. Like, it'll eventually make sense of the word in the triangle. All right, so I think we have all the ingredients now. It's sort of a matter of putting it together. So let's start here. What is the net down component of vector r? Here's where it is very important to be mindful that this 11 is negative relative to the 3.7 meters up from n, right? In other words, you say, hey, just add them up, right? Just resolve them, add up the x's, add up the y's. But if you're not mindful that like down opposes up, and therefore one is negative relative to the other one, then you won't get the correct answer here. So like drawing a picture is one of the best things you can do in physics. If you got a physics problem, if you can sketch it and sort of visualize it. And sometimes you have to visualize it with like symbols, like this represents the trajectory of an object, and we can mathematically sort of break it down like this. And that's a very powerful way to kind of, you know, go about our work here. So what is the answer right here? Let's call it the r sub y, the y component of r. Anybody got it? Call it out if you got it. Okay, if you're wrong, then you'll be right.
Negative 7.62.
If you like negative, sure. I'm just going to call it 7.62. In other words, like it's 7.62 down, right? And we're assigning, you know, there's nothing wrong with it, you know, keeping the negative sign. This is negative. And it reminds you that, like, oh yeah, there's a net sort of this direction. But the direction I assign is negative is down. Okay. The important thing is you didn't add them. You didn't go 11.3 plus 3.7 is 14 or whatever. Right? Like you have to make this sort of negative opposing the other. All right. Because the language of this is just like add them up. But sometimes you have to add negatives, right? You have to subtract. So when vectors oppose each other, that's what's really important. Vector V brings us down more than vector A brought us up. So these are two displacement vectors. It's like one moment, an object went 7 meters this way. And the next moment, the object went 15 meters thusly. Where did it end up? Okay. Well, if the distally and the thusly were, 32 degrees above horizontal and 49 degrees below horizontal, then we can work out exactly the net displacement, the net change in position, and the angle. So we should probably have like this angle right here also. Because if we're doing sort of everything relative to like the positive x-axis, then like, well, where does our point, sort of when all is said and done, sort of relative to that? So we should calculate that angle also. So far we know that there's 7.62 meters of y displacement, so it's a net downward. A brought us up 3.7. B brings us down 11.32. That's a net of 7.62 down. What is the prescription here? Get it? RF? I know it's not for me. Doesn't have to be. But what is the value? Funny or not? .74. I dropped the 4. Okay, 15.74. We could just thought 16. Oh, or someone could obviously. Note that both vectors A and B brought us to the right. So we don't have the same sort of situation where, we got to subtract one from the other, right? Both vector A, I mean, it's visual. That's why I say draw a picture. You can see the vector is bringing us to the right. It also brings us across to the right. So does vector B. This happens to bring us down also. So we deal with the ups and downs here. We deal with the lefts and rights here. We're both right, so we just add them. Now we've got 2 legs of a right triangle. What's the next step? Once we're all done with this, you're going to want to go back through all your working right now and kind of summarize. Think about this simple question. Say, hey, yeah, I just used some resolution of vectors to add 2 vectors A and B. What all did I do there? And so try to sort of annotate your calculations by sort of revisiting them and going through and saying, okay, step 1, resolve vector A. Step 2, do the same thing with B. We did it backwards. We did it first. Doesn't matter, right? Add them up. And then at this step, you could say like step 4 or whatever, however many steps you want to break that down. At this point, you're going to say use whose theorem? Pythagoras' theorem. Use Pythagoras' theorem to solve for R. So it's not like, if I go 7.62 down, and I go 15.74 over, then I go this plus this. That's my total display. No, it's not this plus this. It's this squared plus this squared equals this squared. So here, computationally, let me see if everybody's okay with this. The last step would be like r squared equals a squared plus b squared. A squared plus b squared equals c squared, r squared in physics. So to solve for r, you take the square root of both sides. So like in one step, you can kind of say like, I can just type a lot of my calculator. Even better though. 7.62 squared plus 15.74 squared, quantity raised to the 1/2 power. Raising something to the 1/2 power is the same thing as taking a square root. But this is just way easier to type in your calculator. So like, okay, I got a calculator, 7.62 hit the square button, plus 15.74 hit the square button, equals, and so the sum of these squares is 305.812. I need the square root of it. With this type of calculator, if I were to hit the square root button right now, it's going to open up parentheses and I have to like type back in that answer. I've already got the 305.812 in there, right? So what I want to do is now raise it. So the caret button, raised to the 0.5, the 1/2 power. Or, you know, I could like write the number down, hit the square root, you know, maybe there's a clever way to like keep the answer and then plug it back in. But raising it to the 1/2 power, same thing, taking the square root. Very convenient little trick there. You want to know it. You should get 17.5 meters. Is this the resultant vector? Is this the resultant displacement vector? Yes or no? George's like hesitantly shaking his head in the affirmative. Any other thoughts on this? It either is or it's not, but why might it not be? And why am I drawing this point out? Because it's not. You know, this is not the displacement vector. This is the magnitude of the displacement vector, right? So vectors have what? Magnitude. It tells how much. It really is 17.5 meters long. But it doesn't give me the vector information. What do I need to calculate still? This angle is 5 meters. So this would be like the angle that it's sort of moving below horizontal. Right? The same way that we sort of oriented this one below horizontal. The best way I can think of calculating this angle theta would be to calculate this angle phi and realize that together they are complementary, right? They add up to 90 degrees. So if I really want to know this angle theta to report my displacement vector, how many degrees below horizontal does R send me? Let's say you send out a team, and these are like kilometers. You send out like a hiking, you know, party, and they go 7 kilometers this way, and then the next, you know, leg of their trip they go 15 kilometers this way. So like, then we got to go pick them up. But it's like, we don't want to go all those kilometers, right? Can't we just take a heading in our helicopter and just arrive at where they're going to be? And this is like what we do with the physics, right? We say, okay, well, they went this far this way, this far this way. Yes, we need to travel. What was their distance traveled? They went 7 plus 15, right? They went like 22 meters, kilometers, whatever. But the displacement was only this, right? So reinforcing that idea that oftentimes the displacement is less than the distance traveled, right? Like it takes less distance, you know, there is less distance between this point and this point, and there is between here to here to here. Right? So the distance traveled is greater than the displacement. But if we're setting off in our helicopter to go pick up our hiking party, okay, we need to know what heading to go in from our starting point here. And so if we figure out this angle phi, because we know everything about the triangle here, right? Like we know the hypotenuse is 17.5 meters. We know this leg and this leg, like we know everything about it. So we should be able to use any trig function we like, our favorite one, to solve for the angle phi. And then we know that phi plus theta here is 90, right? Like these are complementary angles. I didn't draw this one, so that's straight. All right, so there's a 90-degree angle there with both of them. So let's solve this angle phi as the inverse tangent of opposite over adjacent. And so this angle phi is going to be the inverse tangent of the side opposite over the side adjacent. And this was the thing that made me fail a half a semester of college trig. I knew how to like plug in the sides. I knew how to plug in the angle and solve for a side like this, but like anytime it's like, what is the angle if the triangle is this? I was just absent the day that they were like, here's the inverse function. If the function of the angle is the ratio of sides, then the inverse function of the ratio of sides is the angle. That's the way that comes out. So the angle phi here, I have a calculator, and I'll start with this, 15.74 divided by 7.62. So I know the ratio of sides opposite to adjacent is 2.065. This ratio. And then I can click inverse tangent. See that my calculator opens up parentheses, so I should have done this. The inverse tangent of open parentheses 15.74 divided by 7.62. So I get this angle here was 64 degrees thereabouts. And so the angle theta that I'm going to report my final answer of 17.5 meters at how far below the horizontal does this angle, does this sort of vector sort of go? Like what is this angle here? If this angle is 64, and from here to here is 90, then I need what? The complement of 64. So that's what, 26? I do that right? 26 degrees below horizontal. Or below positive. Okay. To answer a vector question, we got to give the vector information, the magnitude, which is Pythagoras' theorem, and the angle relative to some, way we've oriented our system of coordinates. Sometimes it's with the compass rose, it's like north, east, south, west. Other times it's with X's and Y. It could be lots of different ways. My apologies, that's All right, and so this is your final answer, 17.5 meters at 26 degrees below the horizontal. That, and now go ahead and take the time to sort of go back through this calculation and annotate it, maybe try to revisit these simple questions. How can we use resolution of vectors to add vectors? And think about sort of all the steps that went in there and the additional notes that you feel like are important for your future self. Remember, your journal is kind of like your study guide for the exam, open note text. So it's like, what am I going to forget about this when I'm like faced with a similar problem on the test? What note do I need to write to my future self? So it's like, remember to do this, push this button in the calculator. So now's the time to sort of do this, reflect on your learning. Think about these questions, like, hey, how can I connect this with what I already know? If I'm learning some trig, I'm trying to remember that. So, that's familiar to me. I can connect that with what I already know. I know something about it. I for comfort, so that's fine. Okay, I got plenty of them. What am I confused about? How does this work? Sorry, you learned. I'm looking at these reflective learning prompt questions from a moment ago when you saw that hi-fi up there. So these are good questions to always kind of reflect on, after a lesson. What am I confused about? How does this work? What's the evidence being provided? I'm not saying you're assigned for all these. I'm saying this is just something to think about. Okay. So go ahead and use some class time right now to kind of reflect on all this. Try to get a really good answer to today's essential question. And we'll see you next time.